So welcome back. This is the final lectures on jets and more precisely on jet substructure. During this lecture I'll try to briefly cover all the points I have not covered in the previous lectures. So just as a reminder of where we stand based on what we did last lecture, what I showed you is that there's a wide variety of jet substructure tools which are available, and what we saw last week was that it's actually possible to try and learn something about these tools using QCD. So we did essentially two cases. One was the case of quark versus gluon jets, showing that you can either use radiation constraints or multiplicity-based observables. And we showed that it's possible to try and measure, calculate and measure groomed jet masses. We saw the difference between soft drop and modified mass drop on one hand and trimming on the other hand, showing that actually things like the soft drop jet mass are actually amenable to precise calculations in QCD, and that's something that's helpful to compare and do precision measurements at the LHC. So there's a bunch of things I'd like to discuss today. The first one, I'll try to make them order, essentially just trying to have the next one following the previous one. The first one I'd like to discuss is shapes for W tagging. So we've discussed essentially mass drop, measuring the mass, and using tools like soft drop can be used to discriminate from W and QCD jets. Shape is the other method, and I'd just like to sketch essentially one way of understanding how this works. I think from here I'll move into machine learning and deep learning kind of arguments. It's kind of a natural follow-up, and based on that, I'll carry on with a bunch of let me call this advanced observables. One message that I want to convey here is that there's essentially different ways to do jet substructure. Doing that from either a pure conceptual point of view, trying to propose a new method based on your intuition of what the physics is. Doing that from a QCD point of view, trying to understand what said method is doing. And machine learning methods have actually been bringing different questions. And at the end of the day, there's kind of a synergy between all these different approaches, and people have devised ways to actually be helpful in all these categories. I'll briefly comment on substructure for Monte Carlo development and heavy ion collisions. That's going to be quite brief, I think, essentially just giving you the idea behind it. And finally, I'll talk about curiosities and a few plots. Depending on time, I hope I'll be able to cover all of this. So the first thing I like to do is essentially discuss shapes for W tagging. So for this, I'll just need, I'll use two objects. One is the n-subjettiness ratio, tau2-1, and tau2 in this case is defined as the sum over all particles in your jet of Zi times the minimum of the distance between, well, so let me call theta, because now it's defined, between theta and axis 1 and theta and axis 2. This depends, of course, on how you decide to choose your axis. I don't want to enter into these kind of details. I'll just give you some examples. That's to some power beta. And typically you use tau2 divided by tau1, tau1 in that case being just the sum of Zi theta I to the beta. So that's one I'm going to use. The other one is essentially based on correlation functions, which is defined as the sum over I, j, and k, Zi, zj, zk, theta ij to the beta, theta ik to the beta, theta jk to the beta. So that's something we've seen 2 weeks ago. These are two shapes that can hopefully constrain radiation, and I'm going to assume the mass of the jet is fixed. So imagine the mass is constrained. And again, I can't do that because I'm looking at W's, And so you expect, if you want to look at W's, you'll first impose that the mass of your jet is around the W mass. And so even if you look at signal or background jets, you can assume that you work with jets where the mass is around the W mass. So let me assume the mass is fixed. Remember, the mass is essentially the sum of Zi theta I squared. So you recognize elements like that here. And for simplicity, I'm going to use beta equals 2, so that at least the angular scaling in these guys resembles that of the mass. And that simplifies things greatly. All right? So again, we want to do leading log. So I'm going to assume strong ordering. And in particular, is strong ordering in angle and in Z theta squared. So if I take 2 Zi theta I squared, one is always much bigger than the other. And so the dominant one, there's one Z1 in particular, there's one Z1 theta 1, which is such that Z1 theta 1 squared is much larger than all the others. And so that's the emission that would dominate the mass. So assuming strong ordering, I can already tell there's one emission that dominates the mass, and then there's all the rest, which is at smaller masses, if you wish. So if you do this, what you can show, it's actually sort of a back-of-envelope calculation, provided you have a decent choice of axes. And again, I don't want to enter into the choice of axes, but you can imagine what a decent choice of axes is going to do, right? You have something, say, which is a W, or a QCD jet, and say this is the emission that gives you the mass. You want to constrain the radiation on top of these two guys, so you expect one axis to be aligned here and one axis to be aligned there. So that's your intuition of what a good axis is. You want to measure radiation on top of the dominant splitting that gives you your jet mass. So in this case, the axis would be, in case of the WQQ bar, the two axes corresponding to the W to QQ bar decay. In case of an emission in QCD, like the one I'm looking at here, it would be the leading parton and the emission that dominates the mass. So leading parton, let me call this 0, and the one that dominates the mass, I've already decided to call this emission 1, okay? So in that case, we can show that this becomes the sum from I bigger than 1 of Zi theta. Well, in that case, it's going to be the minimum of theta 1, theta I squared, theta I 1 squared. So this is going to receive contributions from all the emissions starting from the second, and you're going to you're essentially going to say emission from one prong is going to be from the first prong. So emission from this prong is going to cluster with the dominant prong. Emission from one is going to be cluster for the second one. And again, at leading log, you can replace the sum with the max. So it's just the max of Zi min theta I squared, theta I1 squared. So again, I don't want to do a calculation with this. I just want to make a visual representation of what is going on. So what you're going to have, I'm actually going to use this kind of Lund plane all over the place just to give you an idea of what's going on. So I tell you I have an emission 1 which dominates the mass, which means I have an emission 1 which is somewhere here. That's the mass. And you know that by definition there's a veto for emissions larger than this. That's what we did 3 weeks ago. Now what this does is there's two options. Either the emission is collinear with the leading emission, so I have an emission which is collinear with this one, or I have an emission collinear with the other emission. This is something we never looked at before. I need now, so for all the things we did in the past weeks, the only emission I needed to consider were QED-like emissions from the leading parton. Now, in this case, since we have two branches, you also need to consider emissions from the second branch. And in this kind of pictures, one way of usually representing this is actually as a transverse plane. So if you have an emission which gives you the mass here, you can view emissions from this guy as essentially becoming in a plane which is transverse to the one. They view it as taking perpendicular to the plane. And so all the radiation coming from this first emission here can be viewed as arriving in this other plane, okay? So for all the emission which is, imagine now I want to put a cut, tau 2, 1 bigger than some cut in tau. or smaller than some cut in tau, saying there's less radiation in W than a QCD jet. What you're essentially going to say is I'm going to put a constraint on the maximum Zi theta I squared that I do have in my jet. So this is just saying I'm going to put an extra constraint saying if I have a cut tau here, I need no emissions in this region here. Because an emission here would contribute to this guy for more than the cut I want. Now this would be for the contributions which are collinear, which are, say, primary emissions from the quark. Now if you have an emission from the gluon, you would have a similar kind of cut in the transverse plane, okay? Now this is for QCD jets. And you see that does exactly the job, right? If you have a cut, you have an extra Sudakov veto. You'll have an extra Sudakov veto associated with these regions, which means you're killing your signal. You're killing your background. And you're killing your background hard because this is an exponential subtraction. Okay, so you're exponentially suppressing your background, which is good. Now the problem is that what happens for a W, okay? A W will essentially have a splitting W to QQ bar where both Z fractions here are finite. It's not like this case where this Z is actually much smaller than this. In case of of a W, the two fractions are the same, meaning what happens for a W is essentially what you have is two emissions, the Q and the Q bar, which are both somewhere close to your Z equals 1, which is up there. So what a W would have is, give or take, two of these secondary planes. One, well, essentially the plane there which corresponds to the gluon, you'll have one for the quark and one for the antiquark. And you see again that would give you, in each of these planes, that would give you a small suppression. That small suppression is the same in shape as the suppression you have there, and there's two main differences. The first one is that this Sudakov here comes from a gluon. So these Sudakovs come with a Ca, while this one will come from a Cf. So the Sudakov with a Ca is better than Sudakov from a Ca. That's exactly what we did last week in terms of quark versus gluon separation. Now again, this region here is much bigger than one of these regions there. Essentially the radiation here can go at all angles. QCD can, radiation from this line can come from anywhere along this line, so even at large angles. While if you have a radiation from one hard quark in a W, it's only limited to small angles below the decay angle of the W. So again, this region there is also going to be smaller. So at the end of the day, the reason this shape works, they have a drawback in a way, because both the signal and the background will have a Sudakov suppression, the same way that quarks and gluon did have a Sudakov suppression last week. So this is actually putting a strong constraint on the signal as well. But since the Sudakov exponent, the area which is constrained is much bigger for the signal, much bigger for QCD background, it means that the QCD background is suppressed much more than the W signal. And so that's essentially the idea behind these shapes. Now, if you want to have an efficient shape, the larger the constraint you're going to put here, the stronger your background is going to be suppressed, and so the better the shape is. So if you do this calculation for E3 here, what you're going to find is up to some constant, so up to factor Z1 theta 1 squared to some power, what you find is something like let me put it this way, the max of Zi theta I squared times the max of theta I squared theta 1 squared. That's what you're going to find. If you make the same kind of simplifications I did here, that's what you find. So this means that if the angle theta I is smaller than theta 1, you essentially get a constant theta 1 in front of it, but the shape, so for angles smaller than theta 1, the constraint is also going to be a constraint of the form Z1 theta 1 squared, Zi theta I squared, so it's also a constraint like this. But now, if the angle theta I is bigger than theta 1, this is Zi theta I to the fourth, as a Zi theta I to the fourth actually a shape like this. So again, for the case of the W, all radiation in the case of the W is going to be at smaller angles. So the difference between this and this is essentially just factors constant θ1. While the big difference between these two guys is that if you look at what's at larger angles, which is only present in the background case, you do get an extra suppression here. So what this tells you is essentially that in terms of performance, things like D2 or C2, which are based on angular correlations, are going to have a better performance than tau2-1. Mostly because there's a bigger Sunakov suppression in this region. Okay, so this is the logic. Now, again, this is a perfect example. That's why I wanted to start with this. It's also a perfect reminder of something we've said many times, which is that there's a trade-off between performance, in this case D2 is better than tau2-1, and resilience against soft and large angle non-perturbative effects, for example. Remember, there is somewhere here there's hadronization effects, somewhere in this corner there's underlying event effects, and you see that the bigger you dig into this region, the closer you get to non-perturbative and underlying event, or pileup issues in that case. So it also means that if this is bigger than that in terms of performance, it's also going to be more sensitive to hadronization and non-perturbative effects. All right? So that's essentially that's the only thing I wanted to say about these shape taggers. It's definitely more complicated. It's exactly the same. It's exactly the same. So Higgs into BB bar versus gluon into BB bar. Well, Higgs into BB bar versus QCD jets. The only complication you have in the Higgs case is that it is intertwined with B tagging, if you wish. So the minute you put in B tagging, things become a bit more complicated because you have to, well, the background is not only going to be quarks and gluons altogether. You need to factor in your B tagging efficiency. So you'll have essentially the quark background, which is typically the dominant one, is going to be suppressed by your B tagging efficiency. Well, it's going to be your B tagging miss rate. And the gluon to BB bar is actually a bit more special because the gluon to BB bar is essentially only finite. Glue to BB bar has no soft divergence. So again, there will be a trade-off between glue to BB bar and glue to glue where you have a double mistag. So the case of the Higgs is conceptually there's well, technically it's similar. It's more involved because there's all these discussions with B tagging. You could do the same with Z. You could decide to say Z tagging Z, separating Z from W's by saying I'm going to tag only Z to BB bar. That would be the same thing, yeah.
Just a question. Once you do all that, to study the W, what can you learn? Properties of the W that you cannot do just from the electron decays and favor physics?
You learn absolutely nothing in terms. I don't think you learn much in terms of well, nothing. Maybe an overstatement. You don't learn much in terms of the W. What you do learn, what you do open is the capability when you search for something that decays into a W. So any a BSM case or so a heavy resonance decaying into two Ws, you are essentially opening access to 2/3 of the of the statistics because the W decays 2/3 of the time into jets. So yeah, it's mostly a question of being able to take advantage of some fraction of the data. Yeah. Now there are questions whether you can measure, using these kind of techniques, measure the polarization of the W, because you know that standard model Ws are essentially transverse. BSM Ws some models can give you longitudinal Ws. And so if you can measure the polarization of the W using observables different than this, obviously, that might help as well. It's more complicated. So essentially this is the basic setup. Now what you want to do at the end of the day is have a tagger which is at the same time something which, so let me carry on with the case of the W. You want something that finds two prongs, soft drop for example, plus something that's a shape. So what I've done here is mostly just the shape alone, assuming a constraint on the plane jet mass. Now the combination here becomes a bit more involved if you start saying, no, instead of just having a constraint on the shape, I have a constraint on prongs plus a constraint on shape. This is doable, but it's just a bit more involved as well. So at the end of the day, there's also questions of what you do. Do you compute the shape on the jet after having done the grooming? Do you compute the shape on the full jet? The shapes are usually ratios, what you do with the numerator and the denominator. There's all sorts of complications in here. And I think at the end of the day, that was one of the motivations. So one of the motivations to go into using QCD to look into these guys was that things were becoming a bit messy. There were too many observables to keep track of. It was not clear what Monte Carlo was telling, and I'll show you an example hopefully later. And so trying to search for an ordering principle using a conceptual view of what's better using QCD. Now, this goes a little bit into the same direction. There's many things you can do, and studying everything in QCD is actually a right pain. You have to do essentially a separate calculation. It's hard to automate all these calculations. You need to go and look at observables one by one. So it's not totally obvious to see exactly what happens in QCD, and also in terms of performance. So people started to look into something slightly different. Let me try to avoid the shade. Which is to say, at the end of the day, what we want to do is a classification problem. We have W's on one side versus QCD on the other side. I'll again keep using that. Or quark versus gluons, or top versus QCD. And at the end of the day, this is the same kind of classification problems. That's what you do if you want to classify dogs from cats. Or I don't know, Donald Trump from any reasonable human being. That's a classification problem, right? And we know that there's been a huge amount of developments lately in trying to use deep learning techniques to do this kind of simplification, this kind of classification. So the basic idea is the same. Can I just try and feed a neural net pictures of W jets, pictures of QCD jets, and at the end of the day, let the machine decide whether it's most likely one or the other, okay? And the question is, I'd like to walk to you about what are the pros and cons of this, what are the challenges of this, and what are the main ideas. So I think machine learning techniques have been around, at least in particle physics, since ages. The experiments use boosted decision trees kind of thing since a long time. I think the main difference here is really the use of deep learning. You use actually much bigger networks than you used to have in the standard kind of analysis. And the bigger the network, the more it looks like a black box. Okay, I guess that's the that's essentially what's behind this. The question is, what do you need to decide in this context? You essentially need to decide the inputs. What kind of data do you give to your what's the format of the data that you give to your network? You can make images. I don't know. Look at the energy deposit of a jet in a transverse plane. Transform the energy deposit into a color intensity, and really look at your jets in the rapidity phi plane, and each of the make some binning in there, and each of the cell is essentially colored according to the amount of energy that you have there. You do that for W, that makes an image of your jets. You make sure you align them and rotate them to avoid shifts and biases. And at the end of the day, you can just use the same approach as discriminating cats from dogs, sorry. So that's one approach. You can use a set of shapes. Tau 1, Tau 2 with different values of beta, E3 with different values of beta, the mass using trimming, soft drop, mass drop with a variety of beta and Z-cut parameters. You make a family of shapes and you use that as an input to your network. And we know this is also motivated in the sense that we know that these shapes individually are good discriminant. Then you make a vector of them and you feed them to a neural network. The same way you would probably do in a boosted decision tree to decide the best the best cuts on a handful of shapes. You can use directly all informations on subjects. I don't know, feed all the trimmed subjects in the case of trimming. You can use information about clustering trees. Do feed the whole clustering history of your jet. That's been done as well. You can use directly for vectors. At the end of the day, your jet, that's essentially the most complete thing you can do. Your jet is a bunch of 4 vectors, okay? At the end, that's the whole information you can get. So that's the kind of things people have tried, and together with the input comes the question of the architecture. The architecture of your neural network, and typically this is also something where people can borrow information from computer science, which studies, depending on the kind of input, depending on what you're trying to achieve, what's the best suited architecture to do that. And so in this case, you hear things like deep, dense neural net, connected neural networks, generative adversarial networks, some long short-term memory networks. There's a bunch of objects like this, which tend to be used in the literature those days as well. So essentially, that's the variables you can play with. Then, of course, each of these guys come with different tuning knobs, I would say. You still need to design a cost function at the end of the day to really see what you want to achieve. And the cost function, for example, can decide to ignore certain parts of the phase space or to enhance certain parts of the phase space. So I think, in a nutshell, this is what's going on. This is what it takes to build a machine learning model or a machine learning classifier. Let me make sure I didn't forget anything here important I wanted to say. I think this is about okay. Yeah, and that's about right. So I guess the big question here is, what do you seek? What are you after when you do something like that? And so imagine you try to make a separation of a family of cat and dog pictures. So what you're going to do is have a library of dog pictures, a library of pictures, and for some sample you know the truth, okay? You know this is labeled as dog, this is labeled as cats, and you know the truth. You're going to feed that to train your network, saying try and reproduce which are cats and dogs, and you give him a treat when he's right, and you hit him when he's wrong, until he's learning what cats and dogs are, and you test your validity on a separate sample where you can check whether your network is able to say, to recognize dogs as many times as possible and failing as little as possible when it's a cat. That's essentially the kind of, you can view this as a ROC curve, the way we've done for physics, for W, for any kind of boosted object discriminating before. You really want to maximize your efficiency at tagging what you want to, at recognizing what you want to recognize, and minimizing the failure rate of flagging as a dog anything which is not a dog. Okay? So this is really the game. What you want at the end of the day, what you have in mind, I think, when you do that is really performance. You really want to be as efficient as possible in trying to separate cats from dogs, Ws from QCD jets. So in terms of the ROC curve, if you put your efficiency, your say W efficiency versus your QCD efficiency, what you want to do is have something which is as low as possible in this context. So for a given fraction of, for a given signal event, for a given rate of W jets you will flag as W, you want to flag as little QCD jet as possible. So this is really what this is going on. And essentially, you can view a deep network as a model of a function, as a big fitting function with many, many parameters. And what you do at the end of the day is really trying to get the best log likelihood discriminant, as close as possible to the optimal log likelihood discriminant, which we know is the best discriminant statistically speaking. And so you really try to optimize to get the optimal discriminant in terms of performance. Again, I'm trying to brush the big picture here. There's definitely ways to steer away from this, but I don't want to enter into those details. So you're essentially seeking performance. And that's what you're getting. At the end of the day, what these methods give you is performance. So in terms of, one can easily see the appeal here. At the end of the day, what you want to do at the LHC now, what everyone is desperate for, is finding something new, finding BSM in whatever form. And so this is really extracting the performance as best as you can. This is, in terms of making a search, that's at the end of the day what you're after, trying to get as many signals as you can. As much signal as you can, as little background as you can, so your significance explodes. The question is, what are the caveats? All caveats are dangers. Does anyone have an idea here?
How do you get the errors when you do this?
That's one. How do you estimate the uncertainty?
Sample by using the previous method.
Yeah.
Then you get the sample.
Yeah.
And then you.
So yeah, you need a trailing sample. So you need a sample where you're able to flag things are cats or dogs, or Ws or QCD. And what's the way we know how to do this is essentially using Monte Carlo. So this is typically using Monte Carlo. And then there's a question whether you trust your Monte Carlo enough so that at the end of the day it can be a good way of modeling the data. So this is really a modeling uncertainty, if you wish. So this is something that, I think in a way, this is something that experimentalists are used to do in a way. Whenever you have an uncertainty, you try, well, there's all sorts of systematic uncertainty which enter any kind of measurement. So getting this kind of uncertainty is, if you wish, you can view this as just one extra source of systematic uncertainty. It's a source of modeling uncertainty whether your model of the discriminator is a good model that models correctly, that means that models correctly what the real data is, or whether you don't trust it that much. So the typical approach here is essentially you run Pythia and Herwig, so run two different Monte Carlos, you train your neural network with Pythia, and then you test it with Herwig. And if there's big differences between Pythia and Herwig, it means there's huge uncertainties. And again, using differences between Pythia and Herwig is something that's been around since ages. There's also, so one thing I like to maybe put in perspective is that with all these caveats come challenges. And so one thing I'm going to try and do, I've failed already, is for each of these topics, since the last lecture, trying to give you a little bit of a feeling of what's today's, say, open problem of what today technology. So let me jump back to these kind of things. Essentially, the number of combinations like this we're able to calculate is, one, limited, and two, precision is not great. So doing precision physics with these kind of things is, well, just doing physics with this kind of thing is actually quite limited, and doing precision physics with these kinds of things is limited. So there's definitely room for improved QCD calculations for this. In terms of going back to the matter at hand here, there's generally some say, data-driven approaches that you want to use here. Avoid Monte Carlo. There's data-driven approaches, also unsupervised. Method using unsupervised learning, which are not these kind of which doesn't use this kind of idea here of using a Monte Carlo sample again. There was actually a machine learning conference for JETS something a couple of weeks ago in New York City, and apparently this was one of the big topics of the conference. So the uncertainty is one. The uncertainties also come with well, the uncertainties also come with the dependence on the sample. I don't know. At the end of the day, this question sort of holds in that case as well. Imagine you want to make W versus QCD. A W jet or a QCD jet depends on what you're looking at. If you look at a jet in a Z plus jet process, it won't be the same as if you look at a jet in a 5 or 10 jet event. So there's a question of what, maybe a deeper question of what W versus QCD mean. W versus QCD means something precise if you know a given signal in a given background, a given signal process, and a given background process. In general, this is a bit more complicated. And yeah, so this is something you may want to address as well. Maybe in the same context, there's the question of Monte Carlo imprecision. Let me call that Monte Carlo mistakes. At the end of the day, every single Monte Carlo we have today, Pythia or Herwig, is, or even Sherpa, today's Monte Carlos are only leading log accurate. They have a bit of next to leading log in them, but it's mostly leading log accurate, sometimes even with mistakes at leading log, differences at leading log. And they're limited. It might be that if you train neural network, they're so good at seeking performance and then finding difference in details that they might actually be getting some of their performance from mistakes in the Monte Carlos which are not present in the data. So again, this is related to what I'm going to cover later. It means that we need to develop Monte Carlos in a way that these mistakes are removed. And then again, is there any way that QCD can tell you something in that context? Machine learning seems to be kind of opposite to saying I'm going to make a QCD calculation. If you yeah, so this is also, in my view, an open question, and that's something that Giovanni up there is starting to look into. So I think for all of these points, that it means there's work to do. And so this is really something that people are starting to look into now. Let me make sure if I had. Yeah, so there's been progress. There's progress in this context. There's also progress into uncertainties estimation. Generally methods to be able to put an error estimate, an uncertainty estimate on top of a neural network. Mistakes in Monte Carlo is also related to this unsupervised learning because you stand away from Monte Carlo. Sample dependence, you can try to devise, you can try to be intelligent and say, I expect, go back to the case of quark versus gluon. You expect differences in this, you expect that the Loon plane is essentially universal in collinear physics. Collinear physics is mostly process independent, while things which happen here are going to be more process dependent. So you can try to devise a cost function, for example, when you try to build these things, or you can try to devise a network that is more sensitive to this and less sensitive to that. And in that case, that probably reduces your sample dependence. So there's all sorts of clever tricks you can use to try and play with these ideas, and that's what people are doing right now. There's also there's also the question that I've essentially talked about quark versus gluons, W versus QCD, top versus QCD. At the end of the day, one thing you may want to do is have something which is quark versus gluon versus W versus Z versus Higgs versus top. And you want to have maybe just a single machine learning technique that instead of telling you whether it's a quark or a gluon, tells you whether it's any of the six. So multi-classifier, the same way you would classify handwritten digits and you're not saying whether it's bigger or smaller than 5, you're saying whether it's a 0, 1, 2, or a 9. So in this case, you can have a multi-classifier which one tool kills them all. All right? So this is, I think this is a bit the status now. There's definitely been a proof of concept that these tools work and give performance. And I think I realized I actually never gave you numbers on this. So I'll do this and then move to something else. I mean, I told you we want to separate A from B, and all these techniques succeed at separating A from B. I never told you how well they were doing, okay? Well, you never asked as well. So, again, these numbers are ballpark because they obviously, remember when we did quark versus gluon last week, I told you these methods is either more robust when you vary the jet PT or changes its performance when you vary the jet PT. So these statements are obviously depend on things like the jet PT, the jet radius, depend on external parameters, and I don't want to really go into a whole crazy discussion. So let me try to start with quark versus gluon. And the numbers I obtained were for a jet of PT equals 500 GeV. I did a quick search yesterday to an R equals 0.4. And it's a study done at particle level. There's a whole question whether you include detector effects in this question or not, because imagine you want to measure, take the case of what I just erased, take the case of the jet mass. The jet mass, if you just use particles, output from the Monte Carlo, the jet mass is extremely well measured and precise. So you can measure the jet mass very precisely. If you switch on detector effects, you'll get all sorts of smearings. And yeah, what you think of an ATGVW is not between 75 and 85, it's actually between 60 and 110. Yeah, I think 65 to 105 is the current window for most of the experiments. And this mostly comes from detector resolution effects. So if you do this, and I'll work at a case where there's 50% quark, so you try to achieve 1 quark out of 2. If you use something like an angularity or the mass, remember all these are essentially Casimir scaling things, they all behave the same way, you get a gluon which is around 15%. So for 1 quark out of 2, you get 1 gluon out of 6. If you do something like iterated self-drop multiplicity or some multiplicity-based observable, you get a gluon around, I think it was 7%, something like that. And if you do a machine learning technique, current machine learning technique, reach something about, say, 2 to 3%. So there's actually quite a significant improvement in here. If I want to do W versus QCD, and for this, I'm actually going to take a higher PT of 2 TeV just for the sake of the argument, and R equals 1. And I'll do that with Delphis. For those who don't know, Delphis is a detector simulator, which is way simpler than whatever the experiments have. So it's a simple detector simulation tool. There's an obvious question whether you trust it or not. As part of this, there's also the question of whether you trust your detector simulation, which again, I didn't want to enter too much into these technical and experimental considerations. So again, working at the working point where you have 1 W out of 2, if you do something like, if you do something like a good shape plus stagger, so 2 prongs plus shape, you can reach essentially a region where you have a QCD around 1%. And if you do neural net, you'll get QCD around something like 0.3%, probably a bit less. I've been kind of pessimistic here. And one of the reasons is that there's really the fact that the shape does a lot for you. W has no radiation at large angle, so W is generally different from a quark. A gluon is not that much different from a quark. Okay, so you'd expect much better performances here. The top versus QCD, and here I'm going to take, there's a recent review, I'll show you a plot at the end. I think my PT is 600 GeV, R equals 0.8, and it's again Delphis. And again, for 50% top, the only number I'm going to quote here is neural net version. I don't have any non-neural net for this setup easily. And again, I don't want to compare apple to oranges. What you get in terms of QCD is around 0.3% as well. I think the top is really one of the examples where all these techniques are amplified, mostly because the top is a very complicated decay. So getting it using QCD, you require actually lots of details to get through. In terms of knowing the QCD nature of the top versus QCD, there's only very few techniques which are known in terms of all the QCD approaches I've given. So there's lots of details, like, I don't know, you essentially want two of the decay products of the top to be compatible with the W, so there's lots of dynamics at play here. And so this is where machine learning, I think, gets something nice. I think the original methods were probably something around a few percent, but without detector simulation. I don't know what it would give with detector simulations. The original techniques like the Johns Hopkins top tagger, for people who want to look into the literature, were, I think, at 50% tops, were around, I think at 40% tops, around 1% QCD. But again, same PT range, but no detector simulation. So this is about the numbers you should get in mind. For a reasonable acceptance, you get a factor 10 to 50 suppression in gluons. You get close to a per mil suppression for Ws and tops. If you remove the detector simulation, this goes actually below 1 per mil. Okay? So message number one, you can actually do a great job. It's actually a great rejection factor, a great discriminating factor you get. And it indeed seems that your machine learning techniques do give you that extra step in performance. All right? So, point one done, point two checked. I'll cover advanced observables, let them sink, and then make the break. So again, the logic is, I think, what are the it's a question which is partially what are more extended substructure tools that you can use. One, tools which are meaningful. So based on the conceptual perception you have of what substructure is doing. And two, which fit into these kind of inputs you could give, which could do multiple things at the same time. In particular, be things nice to give into a machine learning kind of approach. And I think there's been really two of these methods lately that I think are probably better than the others. I'm author of one of those, so that may be a biased view. And one of you, if you remember what we did in the first lecture, I told you in terms of reconstructing jets altogether, there's two big avenues. There's viewing a jet as a flow of energy, and there's viewing a jet as a successive branchings of QCD partons. And one use cone algorithms. For the other one, you use successive recombination algorithms. So these two views can actually still work in the case of a substructure tool. And there's essentially two things that have been done. So viewing things as energy flow, and that's something called energy flow polynomials, or multicorrelators. So an example of an energy flow variable is all these shapes. These shapes measure energy flows in your jet. An example of tree structure is genuinely the modified mass drop technique or soft drop technique. You build a tree and then you find the branching in that tree. This builds something, this is an event shape kind of flow that really dictates, that's based on where the energy goes into your jet. And so one thing you can do is actually build an observable which is going to sum over all particles I1, In in your jet, Zi1, Zin. So it's just generalizing this E3 to an endpoint correlator, And then based on your endpoint correlator, you can build all sorts of angles between those. So what you're going to do is make a product over K of the angle between I, let me call AK, IBK to some beta K. And in this case, the samples AK, the set of AK, BK, and beta K is just the parameters of your method. So for any set of A, B's, and beta, you would get a different angular weighting. So this, you can view this as just a generalized version of the angularities we've discussed before. What you can show is this is actually a basis for the observable. So any kind of function can in principle be represented as a combination of this. So again, in principle, the set here for a given n, all the AKs are somewhere between 1 and n. Beta k's can be exponents, and typically you would take 1/2, 1, 2 numbers like this. And so in principle, this is again a family of observables that you can feed to a neural network. And this has been done and actually shows great performance. I'll probably show you an example at the end. So this is genuinely a way to saying this, I'm going to define all these guys are a way of measuring the energy flow and defining a basis of the energy flow inside my jet. And this again, this can be used to characterize your jets, use as discriminant either alone or in a neural net. The other approach is essentially to go back into this idea that if you have a jet, you can essentially view this as a list of primary emissions which go from large angle to small angles. That's the same technique we've used for mass drop and soft drop, and potentially look at these guys as successive branchings. All the branchings here are actually at angles smaller than the angles at which it's been emitted. That's the angular ordering property of QCD. So what you can do is essentially say, I'm going to cluster my jet with Cambridge-Aachen. 2, I'm going to undo clusterings. And at each step of undoing this clustering, so you have your big jet, you decluster it into 2 jets. At each step, you can actually measure a bunch of properties. The Z of the branching, the angle of the branching, the PT of the branching, the soft PT in the branching, define some angle around the jet axis for this guy. I don't know, there's a bunch of properties you can do. So for A, once you take your jet, you split it into 2 subjets. For this splitting, you can to this splitting you can associate a bunch of kinematic variables, and then you just repeat. So one step will give you one value of these guys. If you repeat, you'll just get a tuple, a vector of these properties. Okay, and again, these properties are give or take all the kinematic properties. Repeat, when you do a clustering, you need to decide on which side you go when you repeat, and typically you do the same thing as you do the same thing as what you would do for mass drop or soft drop. When you decluster, you actually forget about the soft branch and carry on in the hard branch. You could get the whole tree. It would be the same, except that instead of being a vector here, you would get a tree of these guys. Okay, so and actually that's what some people have used. You can get a tree and then use a tree neural network, like GRU networks, for example. I think do that. There's something called ReckonN which does this. And yeah, so essentially what you do get here is really a view of the tree structure of your jet with kinematic properties at each node. And the view I'm going to concentrate on just follows the hard branch because it's easier to represent a 1D object than a tree. And in particular, what you can do is go back to, for each point, you can actually plot the log of 1 over theta I and the log of kti, so zi theta I. And so a given jet would have a bunch of points on this plane corresponding to all the primary emissions. And what you do measure here is really the essentially the Lund jet plane, the primary Lund plane for each individual jet. So essentially what the appeal here, I think, is really this is a tool which has been extremely used in Monte Carlo developments. We've used it all over the place to deal with resummations. Essentially what this does is promoting this theoretical tool to a genuine observable, okay? One of the reasons here, and again, I'll show you plots of this later, is among these emissions, you essentially can tag them as saying emissions down here are probably more non-perturbative than emission up there. Emission close to the edge have a bigger chance of coming from initial state radiation or from an underlying event. So depending on where the emissions are in this plane, you know more or less whether you trust them physically speaking. So I'll show you examples on the plot later. So I think what I wanted to say, the main message here is that based on this whole previous knowledge of how substructure conceptually works, and based on the typical kind of information you want to give to a machine learning technique, new techniques have arisen, and these techniques essentially mimic the kind of conceptual ideas you had for jets in the very first place. So either using energy flows or using tree structure. So this is done, and again, this kind of techniques open the door to actually quite a few new studies. And I'm going to use mostly the Lund plane to highlight some of the things in these two cases. So this is done, this is done, this is done, halfway through, and see you after the break in that case. Unless there are questions.
I have a question. Machine learning looks, I mean, since you input knowledge that you have on QCD when you do the machine learning.
You can live without that. If you just put the 4 vectors of all the particles in the event, there's no QCD in there. It's just the full information. The thing is that the more you get, the more complex the input, the more delicate it is to get to train the network, because networks are usually bigger. To get to understand the systematics. So again, that's the usual trade-off, I think, between performance and uncertainties.
Use too much standard model. At the end, you identify the standard model events, and if you have something new, you miss.
Yeah, that's the main problem of unsupervised things, being able to be sensitive to outliers. But there's lots of progress, really, in the computer science community, which tries to do these kind of things.
Second question is, many events, many things you'd expect some missing PT.
Missing ET, yes?
Missing ET. Now, when you do the analysis, you look at jets at one side and the other side.
Yeah.
Try to look at some opposite. And so, I mean, do you look for, I mean, do you take into account missing PT?
So all what I've done here is essentially located for one jet. Now, if you want to make, I don't know, if you want to make a search for some specific process, yeah, definitely for the whole process, you would put a cut. I don't know. Imagine a cut on something where you have an invisible particle, BSM particle, something that decays into an invisible particle, recoiling against a W, all right? Or recoiling against, a W. Let me put it this way. Imagine you have a process like this. What you would typically do is impose that you have a jet here. So this is, this is a W, and this is an invisible particle. I don't know, I'm sure you can find a model to do that. What you would do is impose that you have a missing ET bigger than some cut, that you have a jet, at least one jet, with PT of the jet bigger than something, and probably the rapidity of the jet within some acceptance of the detector. And so that would be the basic cut. Then what you would do is saying, imagine this PT is high enough that this is boosted. You also put a case that your jet passes whatever W tagger you have. And so in that context, I think the basic, all the approach I've discussed here are here. Then you're fine, you can impose any extra code on top of it. There's no, it's not incompatible, that's what I mean.
When you say that you are a bit theoretical, free prejudice, okay, it's not in neural network, in machine learning, it's not totally true, because I mean, you inject this with your, I mean, with
oh, if you use Monte Carlos are essentially based on, yeah. So, I mean, I agree. Yeah. Oh, there are data-driven methods that stay away from this. Things like topics, classifications, things like that do.
Normally we use a mixture of data-driven
Yeah.
and Monte Carlo.
Yeah, identifying sidebands, for example. There's all sorts of. Yeah, again, I didn't want to enter too much into these considerations because this is generic. I think this is not purely a question of machine learning. But yeah, basic thing is I've discussed the dynamics of the jet. That means that you can still apply all possible other cuts that you want, high energy leptons if you want, or whatever comes on top of this of these cuts. All right. So let's resume after the break. All right, last series. So I got hopefully 3 topics to cover. So I told you that substructure tools, so initially they were mostly done, tagging objects was the main task, and I think it is still the main task, in particular in trying to, in practical applications, experimental applications. Through the years, people have realized that substructure can have good potential beyond just the boosted object world. And there's 2 cases I'd like to discuss briefly, just give you an idea of why substructure can help, if it's not totally obvious. The first one is the case of Monte Carlo generators. Monte Carlo generators are used immensely in particle physics. I think Pythia might be the most cited high energy physics paper every single year, theoretical paper. And so this is approved. Everyone uses Monte Carlos, both experimentalists and theorists. So this is really one tool which is at the heart of today's particle physics. And so you want to be able to constrain it. You want to be able to make it more accurate in terms of the parton shower. You want to be able to get better models of hadronization, underlying event, and all these things. So this is something where, if you think about parton showers are genuinely describing how a jet develops. So by looking at the internal properties of the jets, aka jet substructure, you automatically open doors to try and understand parton shower developments. And just to illustrate this, I'll reuse the case of the Lune plane. If you remember, one of the advantages of this guy is that you know that you have soft and collinear radiation somewhere in the middle here. You have hard and collinear here. So all of collinear physics essentially lives in this plane in a given region. The whole parton shower lives in a region. The final state parton shower lives in a given space. You have, at large angle, you will have increased sensitivity to initial state radiation. In this kind of region, you'll have sensitivity to the underlying event. And at low KT, you'll have sensitivity to hadronization. So in a way, this means that if you can measure these kinds of guys and develop observables which are sensitive to each of these regions independently, you can sort of understand your Monte Carlo independently for soft and collinear, for the final state parton shower, the initial state parton shower, underlying event, hadronization. I'll actually show you an example in the plots. So again, developing substructure tools as ways to discriminate between Monte Carlos, if you wish, and improve Monte Carlos is definitely something interesting. It's actually part of an ongoing effort to go to next to leading log or next to next leading log accurate parton showers, trying to see if you can use substructure techniques to validate your accuracy, where you know you can calculate these guys in QCD, and you check whether your Monte Carlo is able to reproduce these observables. Or you check between observables where if you find something which is sensitive to hadronization, which is highly sensitive to hadronization, then you can use that data to tune your Herwig or Prithia or Sherpa Monte Carlo generator in order to improve your description, improve your non-perturbative modeling. So that's done. That's all I wanted to say for Monte Carlo, unless, again, if there are questions, just ask. The case of heavy ions is a little bit similar. If you think, again, view this as the way a jet would develop. So that's the way a jet would develop in a PP collisions. Heavy ion people refer that as the vacuum. Why the vacuum? Because essentially the jet, the partons here are propagating in the vacuum. There's no quark-gluon plasma created as in a heavy ion collision. You would have a quark-gluon plasma created in the early stages of the collision, and then your jet here is going to propagate through this dense, deconfined QCD plasma. And the question is, what happens? People know now since 10, 15 years maybe, yeah, 20 years, 25 almost, it's only 2020, goddamn, that what happens, imagine you shoot that jet through a dense plasma. What's going to happen? Well, all these guys are going to start interacting with the plasma, all right? They're going to scatter out of the quarks and gluons, mostly gluons, in the quark-gluon plasma. And so this means that the properties of the jets are going to be modified. And again, we're speaking about the development of the QCD-based development of a partonic cascade. Measuring how this cascade is modified is going to give you information about how this interaction is going. So again, by measuring properties of the jet, you measure properties of these branchings with and without the quark-gluon plasma, and so you learn something about the interaction with the quark-gluon plasma. That's something called jet quenching. Altogether, jet quenching is trying to measure how a high-energy probe, jet for example, is modified by the quark-gluon plasma. And in this case, what I mean here is that measuring the properties of this, the internal properties of this cascade, helps constraining this guy. In terms of the physics you'd expect, you probably expect two things. One is, well, because of these interactions, you can show, well, one of the property, imagine that you have an emission of a gluon like this. You know that you can, based on QCD, you know that you can view, oh, let me take a case of a photon, that's going to be easier. Take a case of a photon decay into QQ-bar pair. You know from QCD coherence effects that the radiation from this QQ-bar antenna is going to be within all these radiations here. If that's the angle QQ-bar, the angle here is smaller than the QQ-bar angle. That's mostly co-ordering at play. That's a basic property of QCD. Now the thing, the fact that the radiation is mostly within the antenna is a fact that if you try to measure, there's essentially interferences between emissions from one and interference from the other, and the interference between the two radiations is destructive outside of this angle. Now, if you start hitting these guys with a quark-gluon plasma, you're going to break that coherence between the two objects. And if you break that coherence, what you can start seeing is emissions at larger angles. So give or take, the main physical process that's at play here with these interactions is that you'll get extra radiations at small angles. And that's something that you can measure. One, some of these radiation is going to go outside the jet, so your PT of the jet is going to be reduced. Two, there's going to be all sorts of modifications of the jet pattern within the jet. And again, these kind of things is what you want to, you essentially want to be able to calculate this, to find models in QCD to calculate this, and then make measurements of some specific observables that you want to try and compare to your modeling. So there's two things I want to do. One is, at the end of the day, I'm a QCD person. So I want to go back to some funny QCD things. And then I'll show you a flu plots, which you probably can view as a reminder of some of the things I've mentioned and interesting points. So curiosities. The one thing I want to discuss is a variable named ZG. How is this defined? I'm going to run soft drop, And you know, soft drop goes along that declustering, declusters the trees until you find something for which Z, which is defined as the softest of the PT divided by the sum of the PTs. So the Z of the splitting is bigger than some Z cut theta over R. I'll probably take R equals 1 at some point just to avoid fractions all over the place. So you stop at this stage. Essentially, ZG is defined as the Z of this splitting. So ZG is defined, you run the soft drop procedure, it stops at some point, and ZG is the momentum sharing fraction of that splitting, okay? Is that a user-friendly observable? Well, you can quickly get in trouble, right? If you have, imagine you start and you want to start and make a QCD calculation of this. Start with what we did with the mass. You start with a jet with just a single quark. With the mass was 0. You start with a jet with one single quark and a gluon, the mass is whatever it is. In this case, you can do the same thing. I'm starting with a jet with a single quark. That's delicate to measure, right? If you have a jet with a single quark, there's no splitting in your jet, so ZG is ill-defined in a way. Same thing, if you have a jet where all the emissions inside your jet are below the soft drop condition, then again, this is ill-defined. And so imagine I have a jet like this at order alpha, take alpha squared, where I have an emission here which is groomed. Then if I have a second emission here, infinitely collinear emission which is kept and passes the an infinite condition, a collinear emission here which does not pass the soft drop condition. No, that doesn't work. If I have a collinear emission here which passes the soft drop condition versus a virtual correction here which doesn't pass, obviously this doesn't. In this case it means that ZG is ill-defined in this case because this has been groomed away, and ZG here is given by this splitting, because this one passes the soft drop condition. And so that violates one of our basic principles. This is collinear unsafe, because a collinear splitting has modified my observable. It was ill-defined before, and now it has a definite value. So ZG in terms of QCD, if you start making an order by order expansion in QCD, you're automatically into trouble. So people said, let's close our eyes. Let's close our eyes and try to compute this at all orders directly. Let's be brave and try to make an all-order calculation. And so for this, they said, well, the soft-drop condition is always going to stop at some point. It's going to stop at, imagine the soft-drop condition stops at the given angle. Again, the ZG is the momentum imbalance of this splitting triggered by soft-drop. Theta G is the angle of that splitting. You can use the same calculations we've used all over the place, right? You know that if you look back into this kind of plane, if you have, that would be the soft drop condition. If you want a theta G at some value of the angle here, it means that there should be no emissions up there, because if there were an emission up there, that emission would have triggered soft drop first, and so you wouldn't get your targeted theta G. So this is mostly saying that the cumulative distribution for theta G to be smaller than a given value is just it is just as we did before. It's just the exponential of minus the integration between theta G and R Z bigger than Z cut. And again, I'm taking R equals 1. So this would be the leading log distribution of theta G. Okay, that's the same kind of calculation we've done all over the place. You should be able to do this now without even thinking. Now, okay, if I have a given theta G, I can calculate the distribution of ZG. So if I say I do have a given theta G, so my theta G is here, ZG is somewhere along this line here. And the probability of having a given ZG is going to be given by P of ZG there's an alpha s over 2 pi, theta of zg bigger than z cut theta g to the beta, divided by the integration between 0 and 1 dz p of z alpha s over 2 pi that's just the along this line. Alpha s times p is just the density of emissions along this line, so I just get one point along that density. And so this is just the bias formula, right? If the probability of getting Zg is just going to integrate over all possible theta g times the probability of getting, well, you can transfer that into a probability, right? You just take the derivative with respect to theta g here times the probability of getting theta g. And so that's d sigma. Well, that's a derivative of this. I'm going to come back to this in a moment. Times the probability of observing Zg given theta g. Haven't done much, essentially. I'm saying instead of measuring Zg directly, I'm first going to measure theta g. And then I have a probability distribution for theta g. I know for a given theta g what my Zg distribution looks like, and so I can find my overall theta g distribution. Sorry, Zg distribution. Okay, what does this give? I'm going to simplify this. So first, this is perfectly fine. This is finite. There's no more problems in here. I mean, I do have a distribution for theta g, which is bounded. It turns out it's Sudakov suppressed. So essentially, when the angle goes to 0, the Sudakov is going to cancel everything. So this distribution p of theta g, if you look at p of theta g as a function of theta g, it just goes to 0 when theta g goes to 0. So I have a well-defined p of theta g. I have the well-defined probability of Zg as a given theta g. And so this integration is perfectly finite, perfectly fine. This is amazing, right? Well, curious, at least. There's something which is ill-defined order by order in QCD. It's collinear unsafe. And the title of the original paper was Unsafe but Calculable. And these type of variables now have been called Sudakov safe observable. These are strange beasts. Essentially, they are the reason why you can give an answer. I'm not saying, we'll discuss that in details behind that in a second. The reason you can have an answer is mostly because once you try and measure these guys, even in a no-order sense, there will be a Sudakov which is going to kill the region which in principle would be unsafe in the finite order. At finite order, you would not get that exponential. You would just get a series of alpha s with all the logs that would diverge when theta g goes to 0. And so this guy at a finite order would not converge because you'll get logs when theta g goes to 0. Now, once you do an all-order calculations, this Sudakov is going to save the day. And I'm just going to give you one example, which is the case of fixed coupling and beta equals 0. I'm going to assume alpha is fixed and beta equals 0. So the soft drop parameter being modified mass drop instead of soft drop. You can quickly see where this goes, right? If you assume alpha is fixed and beta is going to 0, this just becomes z bigger than some z cut. So sigma of theta g just becomes the exponential of minus, let me make sure I don't forget factor of 2. And let me take the soft limit just to be clear. So p of z is 2 CR over z. So you'll get an alpha s CR over pi log 1 over z cut log 1 over theta g. squared. And so your probability of a given theta g, which is the log derivative of this, would just be alpha s CR over, well, 2 alpha s CR over pi log 1 over z cut times the same exponential. That same exponential goes there. That's one. Then your probability here, P of Zg given theta g, is just alpha s is going to cancel. You'll get P of Zg divided by the integration between, now this becomes z bigger than z cut, between z cut and 1 dz P of z. The case of beta equals 0 is interesting here because this guy is independent of theta g. If it's independent of theta g, this guy can be factored out, and you're just left with integration d theta g over theta g P of theta g, which is 1 by definition. So this means that your P of Zg is just given by this guy. And that's something which should surprise you, because we know that essentially measuring P of Zg is measuring the alternating Parisi splitting function. Normalized in one way, but that's measuring the alternating Parisi splitting function. And again, alternating Parisi splitting functions are kernels in a renormalization group equation. They're not meant to be measurable quantities. They're essentially measuring the degree of pseudo-coherent safety, of collinear, they're essentially collinear unsafe objects by definition. So this actually came a bit as a surprise. The way that this observable has received lots of attention because it's essentially a way to measure the splitting function. Now, I think the one thing I wanted to convey here is that there's strange kind of constructions that substructure has brought. And in that context, this Zg is one of them, where you do have something which shows strange behaviors in terms of their perturbative QCD properties. Now, for people who think about perturbative properties of quantum field theories or just quantum field theories altogether, this is actually something which is also probably interesting in the sense that the number I've given you here, I've made lots of assumptions. For example, here I've assumed that the coupling is frozen, there's no non-perturbative correction, so I'm allowed to take the limit theta g going to 0 without any problem, while you know that at some point I'm going to enter some non-perturbative region. And so the non-perturbative corrections of these guys are not necessarily trivial. This is a leading log calculation where I've essentially used in this expression P of z equals 1 over z and kept the full P of z here. There's all sorts of things which, fine, it's calculable. At the end of the day, I got a number. I have an answer. Now, exactly, is there a way to systematically improve on that? Sure, you're going to go to higher and higher orders here. You can even stick in finite corrections in there. But is there a way to systematically organize the perturbative expansion in QCD to have something meaningful where you can actually put an uncertainty on this, including a power correction uncertainty? This is an open question in my perspective, at least. And this is a generic. I mean, this touches properties of quantum field theories in a way. It's really finding a way to organize your perturbative series expansion so that it does make sense. And so maybe it is at least hints at the fact that there may be different ways of organizing the QCD expansion that are not just powers of alpha s, but can actually do a bit more than just powers of alpha s. And that opens also new observables in that context. I won't do the calculation, but there's another one which I find interesting. I'll just give you the answer. One thing you can look at is, so you're going to run soft drop over your jet again. I'm going to run soft drop. And what I'm going to look at is a variable called delta, which is the PT of the jet, original jet, minus the PT of the soft drop jet, divided by the PT of the jet. So essentially, this is how much PT has been, this is the fraction of the jet which has been removed by grooming. So if you do grooming on your jet, you're going to remove this guy, remove that guy, because they fall outside So this guy falls outside, this guy falls outside, remove it, and then you stop with this one here. What we've been doing all the way through. The question is how much PT has been lost by doing this guy. And again, this is something where a priori this is something which is not easy because you can easily view this angle going to 0 in a fixed order calculation, and then the sum you'll have to sum over all emissions, even collinear ones. For positive beta, the z decreases, so you're probably safe, but for beta equals 0, you can have emissions which carry z cut minus epsilon at any small angle, and so you should expect something which is also collinear and safe. So it's a bit the same kind of argument. Again, you can say I'm going to say soft drop does cut at some value that I can compute using exactly the same theta g probability. And for a given theta g, my delta at leading log at least is dominated by among the emissions below the cut, the guy which has the largest z. Fine. This is totally uninteresting. There's one limit which I wanted to quote, is the limit where, again, if you take alpha is fixed and beta equals 0, the answer you get is the probability, well, the cumulative distribution for delta is log 1 over z cut divided by log 1 over delta. That's something strange. There should be one thing which surprises you at least one thing which surprises you in this expression. What would you, if I tell you I'm going to take a jet, I'm going to run a soft drop procedure measuring whatever is outside of the soft drop region. In particular, everything I'm taking beta equals 0. So it's a cut like this. I'm measuring essentially everything here until I stop. You should expect that the more emission, the more radiation you have, the more you're going to lose. So you would naively expect that if you increase alpha s, you lose more. This result is independent of alpha s. It's fixed alpha s. So running coupling is going to give you corrections on top of that which do depend on alpha s. But I don't know, do that in a conformal invariant theory where beta 0 is 0. And this is also leading log. There would be sub-leading log corrections as well. So again, this has to be taken with the same grain of salt as what I was saying for ZG, that there will be corrections and we don't know quite what corrections are. But at the end of the day, this is a surprising result. At the end of the day, this distribution is independent of alpha s, and it's a damn stupid function. Okay? So yeah, that's what I wanted to say about curiosities. The fact that there's all sorts of maybe interesting things. Over something like probably 12-ish years, Substructure has brought all sorts of interest. Precision in QCD, tagging, beyond the tagging properties, precision in QCD, machine learning techniques, interest for Monte Carlo and heavy ions, and also interest in just the strange constructions in pure QCD. I think this is, if you at least get that message or this message from this series of lectures, I would be happy.
Just a question, maybe I misunderstood. Your two curiosities are leading order?
Well, these calculations are leading log. Now, these quantities are measurable.
Yeah, but they are, the two results are leading order.
The two results are leading log. This one is a generic leading log property. This one and this one are specific for beta equals 0, and assuming alpha s coupling doesn't run. So there would be running coupling correction. You can, if you look into the looking inside Jet's book, the curves that are plotted there include running coupling corrections as well. So you can do it. It's not. It's just at the end of the day, this analogy between P and the altarelli splitting function, between the ZG distribution and the altarelli parity splitting function, is slightly violated by running coupling corrections. Now, in terms of consequences, I told you if you go back to heavy ion collisions, I told you heavy ion collisions should produce more soft emissions. So one thing you can do is look at the ZG distribution in heavy ion collisions and see that there's an enhancement in number of soft emissions, an enhancement at small zg. So this is one thing that has been extremely, well, that's one of the latest highlights in heavy ion collisions, that zg is a variable that has been extensively studied, or at least, yes, studied by both CMS and, I'm I'm not sure Atlas did it. Alice measured the number of iterated software appends at G. CMS has the CMS has it as well. So this is something where you can now start and say whether QCD can produce this, and that was something we did with Edmond and Paul over the last 6 months, trying to see if you can understand how this ZG distribution is modified and see whether this is in agreement with what CMS is seeing in Atlas, CMS and Alice. So yeah, this ZG is an observable which has been measured, with a caveat that in terms of just the pure proton-proton baseline, there's the question of I'm not sure I would be really at ease putting a genuine uncertainty band. So this stays in a way at the level of any qualitative kind of perspective. Doing precision physics with this is not yet, is in my view at least, not yet doable. So I wanted to finish this by showing you, I promised you since the beginning, a few plots to illustrate what I've been saying. And unless there are questions that I can answer on the blackboard, I'll move to this. And hopefully that will view this as a review. And so now in principle, you should be able to do research in substructure yourself. You know all the pros and cons, the caveats, the hot topics. So, first guy first. This is essentially a measurement of, I didn't take the published version, I took the preliminary one from an old talk, of the modified mass drop mass. So you take a jet between 1.2 and 1.3 TeV, and this is measuring the modified mass drop, so soft drop beta equals 0 with z cut equals 0.1. You measure the mass, and this is unfolded, this is a genuine measurement, okay? With proper systematics, proper statistical uncertainties, proper unfolding of detector effects, this is a precision measurement, okay? And in this case, the blue and, well, these two hatched regions are QCD calculations. Fry et al. Is leading order plus next to next leading log. Marzani et al., that's our calculation with Lais, who was a student here, for a next to leading log with next to leading order matrix elements. And, well, first you see that there's a great agreement between the two. You see that the uncertainty blowing here is mostly a question of non-perturbative uncertainty blowing on. These include modeling of non-perturbative effects. One thing that you can see, for example, is the difference between the blue and the red here. It's mostly the fact that this is leading order, this is next to leading order. So remember, in this high mass region, fixed order Monte Carlo, fixed order expansion works, and you do see indeed that there's an effect. You also see that next to next leading log corrections should in principle reduce the uncertainty but don't have a big numerical effect. So this is actually a great story. It's something that started from a boosted thing, realize that you can do precision calculations and realize that you can measure it. This is probably the first story. The question is then, can you do physics with that, like extracting alpha S, for example? That's the kind of success story behind this. This is a scary plot. You should be able to read this now. So that dates back from 2013, just before, I think to me that was the motivation to look into the QCD aspects of this. At this stage, at this point in history, people knew a lot of substructure techniques. You see pruning, modified mass drop, trimming, C2 you should know, and subjettiness is here, trimming is here. Gamma QJet is a QJet volatility. I didn't speak about this one. There's different values of beta for the subjettiness and for C2. And essentially people said, we're going to, instead of measuring just using a one variable tagger, we're going to use a two variable tagger. And then they made all sorts of combinations and make a ROC curve for all of them, all vars being essentially taking all of them put into a boosted decision tree. And you should probably stare at this for ages to realize that if you take, I don't know, a mass plus a mass is going to be less efficient than a shape plus a mass, because as you've learned, shape plus mass build on different concept and so gain more. And if you stare at this spot for long enough, probably a bigger, better resolution version of this, you'll see that indeed combination between a shape and a mass is better than combination between two masses. And two masses don't gain much. So all these dashed lines here are mostly all these guys which are combinations between shapes and mass. And I think to me that was one of the motivations to say, let's look at what QCD tells you, because sorting through this and the detail of this becomes a nightmare and a pain. So essentially one of the motivations to look at QCD was to sort through this. So this is the status 4 years after, which is QCD has proven helpful to say this is good, this is bad, this is better, this has caveats. But still, you're left with saying at the end of the day, I want a mass plus a shape, and there's different ways of taking the mass and the shape. And what our QCD studies have told us is that there's a trade-off between performance and resilience. So this is exactly what this shows. It's performance on the vertical axis, so essentially discriminating power, and resilience against non-perturbative effects on the horizontal axis. So essentially 1 over your sensitivity to non-perturbative effects. So you want something which is performant high up and resilient to the right. And essentially all these dots here are combinations of methods. I've highlighted, so you see again that there's a generic trend of going this way, right? So if you increase resilience, you decrease performance, and if you increase performance, you decrease resilience. So that's meant to show you that there's genuinely a trade-off between the two. Now, given that trade-off, there's still things which do better than others. So these points here and there, essentially the current methods, or at least at that time, that was 2017, the methods that CMS and Atlas were using. This was actually a good compromise that we found, essentially the same kind of resilience as those guys, but better performance. Keeping in mind that this is just resilience against non-perturbative effects. There's no detector studies in here. There's no pileup studies in there. It's actually in the same, this is done as for proceeding works. You can look at these kind of things as well, of course. But yeah, this is to illustrate the fact that there's generally this trade-off is seen in the current technologies, and there's a family of points which are actually more promising than others. So I'm just going now to illustrate all these performances I told you earlier: quark gluon, W jets, and top jets. So this is the quark gluon discrimination, quark efficiency, well, gluon efficiency versus quark efficiency. And you see that essentially the jet mass is that dash curve here. That's the Casimir scaling one. And you can read here the kind of 14% gluon from earlier is here. If you do multiplicity kind of things, iterative solver of multiplicity, you do gain. And if you do machine learning, and you should recognize these are the energy flow polynomials that I told you as new observables. That's the multicorrelators, using also some particle flow networks or recursive networks, dense networks. Oh, come on, what's the C standing for? Connected neural networks. You do get an improvement from machine learning. So that's one of the illustrations of this. In this case, it's a gluon rejection and gluon efficiency, so it's 1 minus my epsilon g, so higher is better. Okay? So my numbers earlier come from this figure. This is the same kind of thing for top, where that was a recent study done probably last year, where each curve here is a machine learning technique. So there's, yeah, all of these points are, again, some network-based and subjectiveness variables, some connected networks, some energy flow, energy flow networks, energy flow polynomials, all sorts of particle nets are essentially for vector-based. And you see again that at 50% efficiency, you get, that's 1, of course, that's 1 over epsilon QCD. You see essentially a rejection of a factor 300. So 3%, 0.3% epsilon QCD at 50% quark efficiency, QCD efficiency, top efficiency, sorry. So yeah, that's, yeah. The other thing is that most of these techniques actually are in the same ballpark. There's no uncertainty of this. I'm sure if you try to put an uncertainty on this, it's not clear at all what the conclusion would be. So for the rest of the slides, I'd like to illustrate a few things with this Lune plane thing. I told you the Lune plane is essentially a way to separate different regions where different kind of physics contribute. So this is measuring the average Lune plane density. So what I've done here is essentially take a Pythia sample, measure all these primary declusterings along a Cambridge tree, and for each of those, you can just measure the average density at a given point in angle and in KT. Okay, so this is essentially just a way of viewing an image in your jet except viewing things geometrically, you view things in terms of the proper QCD variables, which are angles and KT. And what you see here is that there's a gradual increase of the density. So going from blue to red is actually increasing the density. Can anyone tell me what this increase going from high KT to low KT means? What you see there is mostly alpha S. The density at leading log, really leading log, the dominant contribution, what you will get is that the density, which is called rho here, is essentially 2 times alpha S of KT corner factor over pi. So soft and collinear radiation is essentially a constant density. That's what I told you from the beginning, right? You can view leading log as just throwing dots, throwing emissions randomly, uniformly in this guy. And the only thing which is not uniform is the running of the coupling, which runs with KT. And you see this, that increases with KT. Same thing, if you go down to a KT around 1 GeV, you get a bump coming from non-perturbative effects. So this is the region where hadronization lives. The fact that you get this turn up here means you have extra emissions in this region, which is initial state and initial state radiation and underlying event. So again, this illustrates the fact that there's lots of well, you do see the physics in here. You can zoom on this. That would be for W. And you see again, this is, there's clear difference between QCD jets and Ws. Ws here is obviously an emission here, which corresponds to the W to QQ bar splitting. There's no emission up here, and there's less emissions at large angles. So this is really what you'd expect to see. No emissions at mass is larger than W, and no emissions at large angles, because you do have the core ordering, and the W does not emit at large angles. Until you hit again some point where, yeah, well, you get an underlying event that starts and pollute you. So a pure QCD calculation would not have things here, and that's again an illustration that the underlying event is at some point going to kill your beautiful idea of imposing no QCD emission in there. So based on this, you can actually train a neural net using these informations here, either using directly the n-tuples for each declusterings or using directly these as images, pictures of Ws and QCD. You can train a neural network, and what you see is that indeed, at the end of the day, what you get is something which is, oh, I didn't take the right, this is not, well, this is actually a likelihood method and not the neural net. Sorry, I didn't take the plot I was intended to take. But anyway, you can see that using, it's actually close to, neural net would give you results close to this. You see that there's indeed a gain in performance. Neural net would be the same, so think about this as neural net. And what you can do is saying, instead of taking all the emissions within my jet, I can take the emissions which are above a certain KT. If they're above a certain KT, that means I'm actually probably reducing my sensitivity to the region where small KT emissions are, so I reduce my sensitivity to hadronization. And indeed, if you increase the KT, you do get something which becomes more and more resilient against non-perturbative effects at the cost of performance. With the interesting point that this curve is above, this essentially the same set of points as the one I showed you before. You get something which has an improvement either in performance or resilience compared to what simple shape would give. So this means that, again, this is likelihood, but machine learning would give you the same kind of thing. In terms of constraining Monte Carlo generator, in terms of non-perturbative effects, this is a plot again. What I've done is take a slice in this. I've taken a vertical slice in this plot. So just look at the density in one given bin of angle and look at what you see. So first of all, you see that there's an increase, which is essentially the running of alpha S. There's a running alpha S until you reach something like 5 to 10 GeV, where there's a bump associated with non-perturbative effects. And again, if you look at parton level, so plain QCD versus QCD plus harmonization versus QCD plus harmonization and underlying event, you see that at high KT, there's very little difference between parton level and hadron level. So non-perturbative effects are small. While if you go down in KT, there's enhanced non-perturbative correction. So again, this is viewing different regions, which you can use to try and use to constrain Monte Carlo. So what you would do is run Pythia, Herwig, and Sherpa, and you see significant differences in some regions, not only in the non-perturbative region, where you do see some differences between the two, but also in the perturbative region. So that means even the parton shower has different properties, and this can be used to constrain it. Everything clear so far? I think I'm slowly reaching the end here. Oh yeah, this is actually last year highlight for me at least. That was a measurement done by Atlas. So Atlas started to measure this guy. Just bear in mind they use the angle, so log 1 over the angle on the horizontal axis, but they use log 1 over z instead of log 1 over kt. But that's the same. This is essentially a measurement of this guy. Okay, so again, I think it's the same kind of story as the one with the mass, the self-graph mass. You can view that you can that there's an interest in these observable, these interesting properties. Then you come and measure it, and this is actually a calculation that's ongoing. This is the status of the calculation a year ago. I couldn't find on my laptop a more recent plot this morning. But essentially, this is a QCD calculation compared to the currently unpublished Atlas data. At least it's a rough approximation of the data. So again, it's taking a slice of constant angle in this plane. You can calculate in QCD. So this would be this plus subleading corrections. Okay, you do a QCD calculation of that density, and you compare the data to the QCD calculation. So again, this means that this tool can do machine learning, can do constraints on Monte Carlos. You can do the same thing in heavy ions and try to get constraints on radiations. You can you can do QCD calculations, maybe, who knows, extracting alpha S from this as well. So this is essentially what I meant by saying that there's a synergy between all these different aspects, which at the end of the day brings you tools which are able to help in more than one respect. So yeah, I think this kind of approach is probably what's going to be relevant in the future, trying to understand, no, we're at a point where you can actually get very interesting constraint. Maybe you can use this to, again, build neural network where you get confidence as well, and that's what I wanted to say. So I think that's all I wanted to say. So I wanted to thank you for coming through and surviving through this series of lectures. I hope it was helpful. Again, there's no next week, so no need to come and see me and ask me to speak about something next week. I'm happy to. My door is open, so if you have any questions, I'm happy to answer and discuss. But at least otherwise, for this series of lecture, that's all, folks.
Maybe time for questions.
Just wanted to see your loop plane, the previous. So here you have a PT of 2.
That's a 2TV one, yeah.
And in the Atlas?
So Atlas, so that Atlas is 500. I think it's been reached to 650. So there's a series of caveats here. First, this is charged particles only. So this is why you get to small values of delta R. It's charge only. There are efforts ongoing, I think both in Atlas and CMS, to try and extend this to using fold information. So correct for, there are ways you can do. You can do track-assisted measurements where you can use tracks to sort of correct for the neutrals. The reason we picked 2TV, so we didn't, in doing this study, we didn't pick 2TV by randomly. I think 2TV is the region where at the end of the high Lumi run, you would get 1 million events. So in principle, this is something that should be achieved. Yeah. No, I mean, you can do it now. You can definitely do it already with, that's with the current luminosity. That's real data, right? This is real data.
Yeah, this is the overall one to what we call...
So this plot is done with a 500 GeV cut. I think they've raised, we're trying actually to produce some predictions for this, some QCD calculations for this. I think it's been raised a little bit, but give or take, it's still below 1 TV. But this was meant to be mostly a proof of concept that you can measure it. You can unfold it, because this is generally unfolded from detector effects as well. So this is a genuine measurement that you could in principle compare with Pythia, Herwig, and Sherba. There's a pub note from this in on the Atlas collaboration site, and they have plots which show similar patterns as what we see here. Namely differences in some regions between Monte Carlo. So it means also that the idea that this can help constraining Monte Carlos is actually correct. So yeah, I think this was one of the perspective. You can probably do the same with energy flow networks, except energy flow networks don't have energy flow polynomials don't have this property of separating the regions. So I think their usage is slightly different. They may be easier in terms of a neural network context, because they form a base, they're well defined. You can order them from importance from 1, 2, 3, number of correlators you put. Well, in this case, it may be a bit more complicated. So I think at the end of the day, each one have their advantage and inconvenience. But I think in terms of constraining and making measurements, this is good. Yeah, so that was last summer. Presented at the Boost conference last July. And as far as I know, the paper is not out yet, the official publication. There's a conf note, but no paper yet. And Alice has been trying to do the same thing in heavy ions as well, but they have very limited statistics. So there's a heavy ion seminar colloquium next week. I think that Jean-Yves and Raphaël organized. Well, it's Juliana who organizes it now, but there's a heavy ion seminar recurring like once every other month. There's one next Thursday, and it's Liliana Polinario who comes and speaks. She may have ideas of this. There was Leticia Apolinario, who spoke about it at some point earlier, and she was involved in that measurement. So that has been presented in Orsay, I think, a month or two ago. Anything else? Good, thanks.
Well, thank you.